All right, welcome. Last talk before lunch, we have Patrick Hayes, who is a co-founder and CTO at SigOpt, and he's going to talk about accelerating model development by reducing operational barriers.
Hi, everyone. Thank you for joining me today. So my name is Patrick, and I'm the co-founder and CTO at SigOpt, where I'm responsible for building scalable solutions for our users and the technical challenges of optimizing machine learning models at scale. And I'm going to be talking today about efficient methods for optimizing deep learning models that are particularly expensive to train, and how that's particularly relevant for resource-constrained teams that have limited access to DevOps. So let's dive right in. For those of you who haven't heard of SigOpt, our mission is to accelerate and amplify the impact of modelers everywhere. We build software that helps you build better models. And in our experience, having access to the right solutions and tools for model development can make the difference between success and failure. And our job is to make it that much more likely that you as the modeler are successful. To briefly go over my background and journey to founding SigOpt, I studied computer science and mathematics at the University of Waterloo. Then I worked in industry at companies like Facebook and Foursquare, developing products to scale to millions of users. And then in 2014, my co-founder Scott and I founded SigOpt after being invested by great investors like Y Combinator and Andreessen Horowitz. What we find is that teams who are differentiating themselves with machine learning today have a lot of great tools available to them. They've invested in tools like Spark for data processing, Jupyter Notebooks for development, TensorFlow or PyTorch as their modeling framework, AWS or Google Cloud as their computation provider, and many more. And we find that these are essential choices for each team, and they can dramatically impact your team's productivity and the impact of your results. And the right choices here typically depend on your data, your environment, your product, and more. And these decisions are going to be different for each team. At SigOpt, we provide a layer at the center of all these tools that scales your team's model experimentation and model optimization. This layer is critical because it introduces standardization to your model development process and reliability and reproducibility of your team's results. And like all great tools, it composes with the other tools that you're already using and doesn't restrict the type of models, frameworks, or compute environment that you're using. And one component of that layer that we provide is a hosted solution for HyperParameter Optimization. If you're not familiar with this term, HyperParameter Optimization is a technique for finding the best version of your model. Hyperparameters are the parameters of your model that you set before you begin training, and finding the right hyperparameters can be the difference between a model that performs poorly and a model that dramatically impacts your business. Some of you may have heard of hyperparameter optimization by other names, like hyperparameter search or model tuning. And it's also sometimes referred to by the method used, like there are naive methods like random search and grid search, or more sophisticated techniques like Bayesian optimization. And we provide a SaaS solution that hosts the most cutting-edge hyperparameter optimization techniques for our users. How does hyperparameter optimization work? We suggest new hyperparameters for you to try automatically. You train your model with those hyperparameters, and you report back to us how well it did on the metrics that you care about. As this process repeats, we learn more about your model, and we find the hyperparameters that are going to make your model the best it can be. This provides a reliable, robust resource for your team to produce high-quality models faster, which can transform your model development process into a more iterative prototyping process. And efficient hyperparameter optimization can be done without ever exposing your underlying models or sensitive training data to a third party. The box on the left is your training data, your model code, and your infrastructure. That remains private. We've made it easy to integrate, regardless of your infrastructure or modeling framework. We want it to be easy to use so that modelers can focus on what they do best, which is developing the models. Here's how this integrates from a developer standpoint. This example is written in Python, but we do support other languages like R, Java, MATLAB. First, you install the client library with pip, and then import the connection into your model code file and insert your API token. Next, you create the experiment right in your model code, and you define the hyperparameters that you want to optimize. So in this example, we're optimizing hyperparameters such as the learning rate and the size of the hidden layers of this network. We support multiple parameter types like continuous, integer, and categorical variables. And you can define a budget here to limit the amount of compute that you're going to use during this experiment. Next, you parameterize your model. This is a slight modification of your existing code where you allow us to suggest values for the hyperparameters that you're tuning. This is also where you define your objective metric that you'll be optimizing. In this case, it's the accuracy of the classifier, but it can be other metrics like an F1 score or whatever else is important to your team. Finally, you include a few lines of code to trigger the optimization loop. This requests suggested hyperparameters from SigOpt, evaluates them, and then reports back to us how well those suggestions did. And we allow, this is a simple serial loop, but we do allow this to be done in parallel across multiple machines so you can get to better results in less wall clock time. And at the end of this process, you have a fully optimized model, and you'll know if it's something that you're ready to deploy to production. And throughout this process, you have access to results on the web that provide you and your team with analysis of how your experiment is doing, and a simple way to track, manage, and reproduce your experiments. This includes a full history of the experimentation that you've done, as well as insights on any individual experiment. And we make this easy to share with and collaborate with members of your team. This comes with a bunch of benefits, but I want to call out a few for you. First, it optimizes your models more efficiently than other methods, which can mean dramatic savings on your compute bill. On the left is a demonstrating comparing methods like SigOpt to methods like grid search or random search, which can cost 1 to 2 more orders of magnitude more on your compute bill to conduct a full optimization. Secondly, it accelerates this optimization process, which will let your team spend more time building more models. And it'll improve the accuracy of each model that it optimizes. Now, there's no free lunch, so we're unlikely to outperform a custom solution built for a specific model. But on average, we outperform other methods when applied to a variety of models. There are some links here, including a blog post on NVIDIA's blog that allows you to explore some of these results in further detail. We spend a lot of time benchmarking and measuring our impact to make sure these claims are as rigorous as possible. What I've shown you here is a relatively simple step-by-step process, but there are many advanced applications of hyperparameter optimization as well. For example, optimizing models where your hyperparameters have constraints on those hyperparameter values. You might have 2 or more metrics that are competing in some way, such as the accuracy of your classifier and the speed of its inference time. And we allow you to conduct optimization in that setting as well. We also allow you to gain insights about your model as your optimization progresses, such as the relationships between your hyperparameters and their relative importances. We spent years building these features into our solution to make sure we can support the types of problems that modelers are seeing in the real world. And that's because these advanced techniques are often needed when applied AI introduces unique challenges. And we focus specifically on solving problems that are encountered in real-world applications rather than theoretical benchmarks. And here are some of the examples that you see in that setting. Your machines might fail, causing you to lose information about a hyperparameter configuration. You might have uncertainty. Perhaps there's noise in the results that you're observing, and more. We cover all of these extensively on our blog, so I won't go through all of them individually. But today our focus is on the last two, models with lengthy training cycles and how to orchestrate your cluster to best conduct hyperparameter optimization for these expensive models. And specifically, we're considering these challenges in the context of deep learning models that are very expensive to train. Some models can take days or weeks to train even a single instance of that model. And we often see that because of this, these expensive models go unoptimized, because the standard methods might take days or weeks to complete. And this isn't just an academic exercise. We're seeing an explosion in the amount of compute that's required for sophisticated modeling. This is a chart from a recent OpenAI blog post. And in short, from AlexNet in 2012 to AlphaGo Zero in 2017, there was a 300,000x increase in the compute required to train these sophisticated models. And we've seen this before. In the 1800s, as coal-burning technology became more efficient, you might have expected the amount of coal that was burned each year to decrease. But actually, the opposite happened. The amount of coal burned each year increased, which is a bit counterintuitive, but it's because as coal became a more cost-efficient fuel source, the demand for it increased dramatically as new applications were made possible. Some of you may know this as the Jevons paradox. So what that means for us is that the problem of lengthy training cycles is unlikely to go away or be solved by hardware innovation alone. As GPUs get faster or other hardware innovations enable us to train more expensive models, more sophisticated models will fill the void, and our most sophisticated models will still take a long time to train. And these types of expensive models are becoming more ubiquitous. We see them in applications like speech recognition, deep reinforcement learning, computer vision, and more. Each of these domains involves complex models as well as huge data sets. And because of the long time it takes to train those models, hyperparameter optimization with traditional methods can be difficult or unfeasible and may not be performed. To put these long training times in context, this is an example. So even with sophisticated hardware, training ResNet 50 on ImageNet might take about 10 hours. This is a real benchmark from a recent blog post. But the actual model and timing aren't so important, as this is reflective of many use cases that we see in real applications. So to optimize 12 hyperparameters of this model, you should be training your model on at least 120 distinct hyperparameter suggestions. So in total, you're looking at about 50 days of total compute time. And the question is, can we do better? When you have the compute resources available, the first thing you should look to here is, can you speed this up with parallelization? Can you use more than one machine to speed up perhaps not the total compute time, but reduce the wall clock time dramatically? This can help you get to a high-quality model in less time, which allows you to ship it to production faster or iterate on the next version of your model sooner. But particularly for expensive models, managing this parallelization introduces more challenges. And how can busy teams with limited access to DevOps manage their compute resources efficiently for these complex model training jobs. Now, this is not always a challenge. In some cases, if you can train a model on your laptop because it's not that expensive, then the DevOps challenge might not exist. You might also find that for simple applications for a single individual, that you also don't need these types of resources. But for teams that are modeling at scale, this often isn't the case. In fact, there are often multiple levels of complexity. At the base level, you might have multiple users on the team sharing limited compute resources. Each of those users might be conducting multiple experiments at the same time, optimizing different models at the same time. Each of those individual experiments might need to train multiple different hyperparameter suggestions of the same model at the same time. And then each individual training might need to be conducted across multiple GPUs. So you have this tree of complexity and these levels that all compound on each other when you might have limited access to shared compute resources. And this presents a unique challenge for teams that are optimizing at scale. Some of those challenges might include launching and managing Kubernetes clusters across different clouds that your team uses to run experiments, scheduling those experiments to run and use the compute resources you have efficiently, conducting hyperparameter optimization across parallelized training jobs, and then monitoring these experiments as they progress, including the underlying infrastructure, and watching for your progress, if there have been any failures, or to alert yourself to anything else that you might need to adjust in the process. As you can see, there are a lot of challenges here with regards to infrastructure, scheduling, and more. So we built a tool called SigUp Orchestrate, which is a command line tool to manage these challenges. It containerizes your models with Docker and uses Kubernetes to train them in parallel across your cluster of available machines. This has many advantages, but notably, it provides a stable, scalable way to submit training jobs to your cluster of available machines and have them scheduled and executed in parallel. The goal here is to provide a tool to modelers that fully abstracts the infrastructure and DevOps so that the modelers can focus exclusively on modeling. I'll show you what it looks like from the developer standpoint. So this file should look pretty familiar. This might be your standard model code, and in this example, it's a random forest classifier, I believe through scikit-learn. And here you replace the hyperparameters that you want to tune with calls to Orchestrate's library, as you can see highlighted in the first box. Then, as you conduct hyperparameter optimization, these values will be replaced with suggestions, and your training will automatically be conducted with those new values. Then, you report the metrics that you care about, as you see in the second box below. This is intended to be as frictionless as possible, to require the fewest changes necessary to your code. And also, the modified code can be run as is without an Orchestrate cluster. So there's no lock-in, and furthermore, it fits into your existing development process. Next, you define a model configuration file. This allows you to define setup code or your dependencies. And here's also where you define the hyperparameters that you're tuning. So in this case, because we're tuning a pretty simple model for illustration purposes, we have 3 integer parameters, the max features, the n estimators, and the min samples. And you specify the ranges that you'll be searching over for your particular application. Then at this point, it's one command line invocation, which you can see at the top, which kicks off the optimization process. This containerizes your model with all of its dependencies and schedules it to be executed across your cluster. At this point, the experiment has begun. You can shut your laptop and walk away. and when all your tasks have completed, you'll have the results on the web. And as I mentioned before, you can run multiple optimization experiments on the same cluster and share these resources with your team. You can monitor the status of your experiments through the CLI. You can see how far they've progressed. So this is an example where we can see that 8 observations have completed, and none of them have failed. And also a link to the web where you can dive into more detail. And you can view your experiment logs as the experiment progresses, separated by the distinct jobs here, separated by color. You can watch this live as the experiment is running, which allows you to watch for problems, or you can inspect the logs at the conclusion of the experiment. And then, as I mentioned before, all the results are available on the web of all the experiments you've run, which allows you to track your history, have a record of the experimentation you've done, as well as monitor the improvement of any individual model. If you implement automated cluster management using a tool like SigOpt Orchestrate, you're solving many of the biggest challenges for deep learning optimization that teams are encountering today. This will set up your team to optimize expensive models that previously may have taken a long time to tune, and increasing the likelihood that these models reach the level of accuracy required to make it to production. So now we can revisit that original example of ResNet 50. Previously, we found that it might take 50 days, but if you're able to efficiently conduct parallelization across 20 machines, now your wall clock time is reduced to 2.5 days. This is clearly a dramatic improvement, and this is how you translate advanced optimization techniques and appropriate use of infrastructure and tooling to translate to real value for your team. If you're interested in this or on any of the other topics that our team is researching, we offer in-depth analysis on our blog, where our engineers provide insights into experiments and ongoing investigations into new techniques. And thanks for your time. So if you're a researcher, an enterprise, or an aspiring student, we have a version of SigOpt that's right for you. If you're interested in trying SigOpt Orchestrate, I'm happy to answer any questions now or individually. And also, we'll be showing a demo at our booth over the lunch break. And I appreciate your attention today, and I'm available for any questions.